Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. Today in this video lecture, we will study about the subject Digital System Design, and we will be taking the very important topic, that is asynchronous counters. Before discussing the asynchronous counter, let us understand the difference between synchronous counter and asynchronous counter. So basically there are two types of counter. First is asynchronous and second one is synchronous. So asynchronous counter is made up of flip-flop. Of course, synchronous counters are also made up of flip-flop, but the synchronous counter, all the flip-flops, they are triggered with the same clock pulse, right? In asynchronous counter, there is a huge difference from synchronous counter, that output of one flip-flop will work as a input clock to the next flip-flop. That means if we are having, let's say, 3 flip-flops, then if we are using making the synchronous counters, we will give clock to all the 3 flip-flops at the same time. But in asynchronous counter, if we are making a synchronous counter, then the first flip-flop output will be connected to the second flip-flop clock input, and second flip-flop output will be connected to the clock input to the third flip-flop. So this is the basic difference between asynchronous counter and synchronous counter. So a digital counter basically is a set of flip-flops, as I mentioned, which can change the states. Now let us understand what are the states of a counter. Let us take an example, that if we are taking a 4-bit counter, then how many states would it will have? So it will have the 16 possible states, right? So what are these states named as? These states are named as 0000, one state, 0001, second state, 0010, third state. Now here one important thing is also that let us design one counter which is counting from 0 to 2. Then it will have 0 counting state, 1 counting state and 2 counting state. That means there are 3 counting states. We can also design a counter which can start from 3 and end up to 5 or any other number. We can start from any number and we can go to any number. Of course, we can skip 2-3 stages. Any type of counter we can design using flip-flop. That is clear. So counters are designing is based on the number of states. That is one important point. Whenever we are designing the counter, we should clarify the number of states which it is taking, and then the whether we are going to give same clock pulse or we are going to design asynchronous counter. And the asynchronous counter here we are going to discuss in this video lecture. In the next video lecture, we will be discussing the synchronous counter design. So asynchronous counter, in this type of counter, flip-flops are connected in such a way the output of the first flip-flop drives the clock of the second flip-flop, and all the flip-flops are not clocked simultaneously in asynchronous counter. Asynchronous counters are also known as ripple counter. So because the first flip-flop output is connected as a clock to the next flip-flop, so whatever be the delay of the first flip-flop for producing the output, that is going to be a disadvantage for such type of asynchronous counters. In the synchronous counter, since all the flip-flops are clocked at the same time, so there would be no delay. Only delay will be the delay of one flip-flop out for producing the output. So all the flip-flops will produce output at the same time and they are clocked simultaneously. Design and implementation becomes tedious whenever we are increasing the number of states in case of synchronous counter. So all the flip-flops simultaneously triggered, and hence propagation delay is only the propagation delay of just one flip-flop. So this is the basic two difference between the asynchronous counter and the synchronous counter, right? So now coming to some brief introduction about the counter. The counter can count up as well as the counter can count down. So it may be a up counter and it may be a down counter. So an up counter will start counting from 0 or lower number and going to higher number. A down counter will start from higher number and will go to the lower number. So the number of states, coming to the number of states through which the counter passes before returning to the starting state, it's called the modulus of the counter. Okay. So the number of counting states are equal to the modulus of the counter. This is also important. Hence, the modulus of a counter is equal to the total number of distinct states including 0 that a counter can store. Okay. So if we are counting 0 to 3, there would be we are designing, that means a modulus 4 counter, right? Each of the count of the counter is called a state of the counter. Each count is known as state, as I mentioned before. In other words, the number of input pulses that causes the counter to reset to its initial count is called the modulus of the counter. Since a 2-bit counter has 4 states, 0, 0, 0, 1, 1, 0 and 1, 1. So we will call it as modulus 4 counter or mod 4 counter, right? So here the brief summary: the number of states through which the counter passes before returning to the starting state is called the modulus of the counter, and hence the modulus of the counter or mod of the counter is equal to the total number of distinct count including 0 that a counter can store, right? So here we are clear with the modulus of counter, the difference between synchronous counter and asynchronous counter. Sometimes these questions may be asked in the examination. So this counter designing, the concepts must be clear. So whenever we are designing a counter, we must start with whether we are going to design a synchronous counter or synchronous counter. Let us start with ripple counter or asynchronous counter. Here there is a diagram for asynchronous counter. We have made a ripple counter, which is a 2-bit counter here in this figure. So 2-bit counter, we are using 2 flip-flops to make 2-bit counter, right? So here let us understand in detail what we are going to do. I have taken 2 flip-flops. We are making a 2-bit asynchronous counter, right? So let us take JK flip-flop, JK designated by first flip-flop as A flip-flop, and this will be the QA, and this is the clock. Okay, let us take negative edge triggered clock. Okay, another counter we will also mention, we will take as negative edge triggered clock the two inputs JB and KB. Right. So here, if you want, we can mention QA bar and QB bar. So this is JK flip flop 1, JK flip flop 2. Right. Now, so we have taken 2 JK flip flops. Just note that we are taking negative edge triggered flip flop, right? Okay. Now to make it a synchronous counter, what I am going to do, I will connect this QA to my another flip flop. Now I have made the asynchronous counter, right? So whenever I am working with asynchronous counter, I have already told that the output of first flip flop to be connected with the input clock pulse to the next flip flop. This is the type of connection we have made. Now let us understand the working of this. Okay. So for understanding the function for this counter, what we are going to do, just okay. So here we will set this JA as 1, KA as 1, JB as 1, KB as 1. Okay. And or you can take T flip flop also for designing a 2-bit asynchronous counter. So here let us take J, K and connect to the 1, 1 state. We know that in JK flip flop, whenever we are giving the input as 1, 1, then there is a toggle state. So working will be only for the toggle step type if we fix JA, KA, JB, KB as 1. So here it will be a toggle. Now we will draw the clock waveform. We will see how the input is coming and the how the output is coming, right? So here we are going to make the clock pulse. Yeah. All the negative edges we will mention. Okay. So this is my clock here. Okay. J is 1, K is 1. So whenever this negative edge will come, then there will be a toggle. Okay. Now assuming the flip flop are initial states QA and QB are 0. And in fact, we are not assuming we are resetting before starting any count. Okay. So what we are doing, we are having QA and QB as 0 initially. So let us, whenever it was QA, it was 0. Initially it was 0, yes. Whenever it will receive a negative edge triggered clock, it will change the state to 1, right? Then again it will drop down to 1, then it will be a 0, then it will be a 1. Whenever negative edge comes, it will be changing its state. Mention all the negative edges here, right? So this is QA. Now coming to the QB, right? Now this QA output is going to be the input to my next flip-flop clock input. So whenever this edge will come, QB will change its state or it will get toggled. So here like this, okay. Mention the negative edges here. So this is the output of my counter. Let us mention all the 0, 1, 0, 1, 0, 0, okay, 0, 1, 1, 1, 0 and 0. So we have written the things 0, 1, 0, 1, 0, 1. The all the for all clock pulse for each time period. This is time period T. This is time period. Let us take the frequency. This one is ST. The time period of this one is T. What I am mentioning here, this is T. This is T in that way. Let us we have applied a clock pulse of time period T and hence the frequency will be 1 upon F. Okay. Here the time period is 2T and hence the frequency of this clock will be 1 upon 2T. Now here the time period is 4T, then the frequency of this clock pulse will be 1 upon 4T, like that. Okay, so we can understand from the waveform that as the clock pulse are increasing their time period, the frequency is getting reduced as F is equal to 1 upon T. Right. So the frequency of QA is 1 upon 2T, the frequency of QB is 1 upon 4T. This part is clear now. Now to understand how it is counting, so we will note all the values for the counter. QB, QA. Here QB, QA 0, 0. Here QB, QA 0, 1. Here QB, QA 1, 0. Here QB, QA 1, 1. And then again 0, 0. So my counting is this. So this is how the asynchronous counter is working and giving us the counting 0, 1, 1, 2, 3. Okay, now this is the kind of counting we are getting from the asynchronous counter. So this counter is known as mod 4 counter, right? Because it is having 4 states it is taking 4 states including 0, it is going through 3 more states, and hence it is known as mod 4 2-bit counter, right? So this is a kind of working for the asynchronous counter. Now, this is the waveform which I explained. I told you we can also make a down counter. So for making a down counter, which can start from counting 1 1 to 0 0, what we do is we take all the configurations are obviously same. We are putting this J, A, K, A and J, B, K, B are equal to 1. This value is 1, right? And here we are giving all the 1 T. You can also take a T flip-flop. Only the point is, in this case, we are connecting Q1 bar to the clock input to the next flip-flop. So, this is the basic difference to design a 2-bit ripple down counter. Now, this is going to start from 1 1 and then it will count down. Like this, it is going to count, right? So, here, see, from this figure, this Q1 bar is connected to the clock input to the next flip-flop, and this is also negative edge triggered. Okay. So, this is the basic difference for making a down counter. We can also have the up-down both counters simultaneously. See, the logic is very simple to design. Since we are taking down counter, 2 flip-flops, so I can hurry it up. Negative edge triggered, right? So what we are going to do is, this is 1 1 1 1 JK flip-flop we are taking, and this we are making a up counter. In case of down counter, we are giving this one. Okay. So, or you better to make this is for up, this is for down. QA is connected to clock input for up counting, and QA bar is connected to the next flip-flop for down counting. So, this is the basic difference between up and down counter. So, what we can do is, we can add some extra circuitry which is able to select either QA or QA bar. To design that, what we can use, we can insert one M input. Okay. Now, M input to be multiplied by QA. Okay. And M input to be multiplied by QA bar, and that should be added. Okay. Now, what is happening in this case? If M is equal to 0, then QA bar is connected. Okay. And if M is equal to 1, then QA is connected. So, in this way, if we take one OR gate and one AND and 2 AND gates and one NOT gate, and we can add to this arrangement, then we can get both up and down counter. See here, the clock signal to the second flip-flop is given by 2 AND gates. One additional input we have taken M is equal to 0 or M is equal to 1. If M is equal to 0, it is counting down. If M is equal to 1, it is counting up. Because when M is equal to 0, the output will be here 0, and this is not going to be connected. If If m is equal to 0, then it will 1, and here this will be q1 bar or qa bar, same q1 qa, same thing. So qa bar, and this is going to be connected and the counting will be down. For m is equal to 1, reverse will take place, and by adding some small circuit of simple circuit of 2 AND gates, 1 NOT gate and 1 OR gate. See, here we are using 1 NOT gate, 1 AND gate and 2 AND gates, right, and 1 OR gate. We can design both up and down counter with the same 2 flip-flops, and the circuit will become easy. So in this way, the 2-bit ripple up down counter can also be designed. One more point I would like to add in this video lecture, that is very important, that if we are giving negative edge trigger, then we are connecting this one to clock input for up counting and q1 bar to clock input for down counting. If we are using, let's say, positive edge triggering, then what we will do, we will connect it q1 bar for up counting and q1 to down counting. This is the basic difference for negative edge triggered clocking and positive edge triggered clocking. That's all for this video lecture. Hope you have understood. Thank you so much.